So first of all, I would like to thank Riccardo and Sylvain for organizing the lectures. The first thing is what this course is about. So the main aim of the lectures will be two. First one, I would like to discuss the typical properties of glassy systems, and in particular I would like to discuss frustration, disorder, and metastability. And these are like the key points that you find in many glassy systems. So this will be like the physics, and the second thing that I would like really to show is techniques and tools. So the second aim will be a kind of overview of tools that you can use to study these systems. And these tools actually are interesting because you can apply them in many different systems, both in condensed matters, for example in glasses, spin glasses, soft matter, rheology. But of course, they can be applied also in other fields, for example, computer science, inference, machine learning, and so on. So the tools I'm going to discuss will be basically three. So, okay. So what I would like to discuss is first the replica method. And in particular, replica symmetry and replica symmetry breaking. Then I would like to discuss the cavity method. Also known in the context of computer science as belief propagation. And finally, I would like to discuss the dynamics, and mainly Langevin dynamics. So the idea of the course is to apply these three techniques to a simple model, that is a model where you have all these properties, that is called the spherical random perceptron. So the model will be so this is a very simple model, and it's a model for it's a constraint satisfaction problem. It's a simple model for glasses. And actually, it has a jamming transition. That is the first application I would like to discuss. So the idea of the course will be to study this model using these three different techniques and to derive some properties of the model. For example, I would like to show you how we can describe the jamming transition. Okay, so this is the plan of the course. oops. So the idea will be, oops. Will be to study the replica method in the second, third, and maybe fourth lecture. Then I would like to do this in the fifth lecture. And then this will be the last lecture if time will permit us to do it. OK, so in this lecture, in the first lecture, what I would like to do is a kind of crash course in glassy systems. It will be very qualitative, no technicalities at all. It will be just a kind of overview of the properties of glassy systems. And so what I would like to do is first try to describe what is a glass. And in particular, I would like to discuss the phase diagram of art spheres. So this will be the first part. And the second part will be what is a constraint satisfaction problem. So this is constraint satisfaction problem. And in particular, I will describe the phase diagram of the random coloring problem. So these are two different, let's say, glassy systems. And the idea is to try to understand what is their relation. OK? So what I would like to show you is that there is a deep relationship between these two systems. And so once we have understood the relation, what I would like to do is to go to the model that we will study, that is the perceptron. And this will be a model that has features from glassy systems like structural glasses or hard spheres and constraint satisfaction problem. OK. So can I erase this?
Sure, sure.
OK. So first of all, what is a glass? Of course, a glass is a solid. So a practical way to define a solid is how it responds to perturbation. So typically, what you have is that if you take a glass and you strain it, so you deform it in some way. So if this is the linear size L, and this is gamma L, and gamma is the amount of deformation that you have applied. So since this is a solid, it will exert a force against the deformation, that is the stress. And if the deformation is small, the stress will be linear in the deformation, and the proportionality factor will be the shear modulus. Okay? So a solid is just a system that has a finite shear modulus. And you can define solids in two classes: crystalline solids or amorphous. OK? OK, so in crystalline solids, what you have is that the degrees of freedom are organized into a lattice, into a regular lattice. OK? So you can imagine that the particles just vibrate around the nodes of the crystalline lattice. Instead, here, particles are placed more or less at random. And what is interesting is that if you take a liquid configuration and you take the configuration of a glass, they will be practically the same. So there is no order that is appearing in the system. So the question is that if we take crystalline solids, we understand how they form, in the sense that we understand that the formation of crystals is actually driven by the fact that you are breaking translational invariance. So in the liquid phase, the system is translational invariant. And when you are in the crystalline phase, translational invariant is explicitly broken because you have a crystalline lattice that is forming. Instead here, as I told you, the configuration of the liquid are basically indistinguishable from the configuration of the glass. So it's not clear what is driving the freezing transition. So since we would like to understand how amorphous solids, what are amorphous solids, what are glasses, what I would like to do is to try to understand how they form. Okay, and so what I would like to do is to take a simple glass former and try to understand how a glass forms. Okay. Okay, so what I would like to do is to take a simple glass former that is our spheres. Okay, so I take a set of n spheres in a volume V, and the interaction potential between two spheres in a position xi and xj is zero if xi minus xj is greater than the diameter of the spheres, and infinite if their distance is less than the diameter. So basically, this is a potential that allows actually forbids the overlap of two spheres. Okay, so if this is the radius, so it's d over 2, a configuration like this is permitted and the interaction potential is 0. Otherwise, you cannot overlap the spheres. Okay. So what you can do, since the spheres are non-overlapping, you can define the quantity that is the packing fraction. So you first define the density. It's just the number of spheres divided by the volume. And then you define the volume of a sphere in d dimension of diameter d. And this can be computed. It's pi to the d over 2 times d over t. And then you have a gamma function. And so you can define the packing fraction and the packing fraction is just the fraction of space that is covered by the spheres. So it's simply phi. It's simply Vd times n divided by V. So it's just Vd times the density. And this is a control parameter. Okay. Okay. Oops. Okay, so now since we have a system of spheres, what I would like to do is to try to understand what is their dynamics. Okay, so first of all, you fix the packing fraction phi, and you fix it in such a way that it is very low, in the sense that it's very easy to find a configuration of the spheres that are not overlapping. Okay. Then you fix the dimension. Okay, so fix phi. Then you fix the dimension. Let's say that we are in 3 dimensions. And then you fix the positions of the spheres in such a way that they do not overlap. And this is possible if the packing fraction is low. Okay, so once you have the positions, xi, you just throw at random the velocities of the spheres, and you extract them from a Maxwell distribution. So this is just a Gaussian. Okay. And then you start to run the Newtonian Dynamics. Okay. So what you do is that you run the equation of motion of the spheres, and the spheres move of free motion except when they collide, or they collide with the walls of the container. Okay. So when they collide with the walls, you just do an elastic collision with the walls. Otherwise, if 2 spheres collide, you can compute the final velocities just by imposing a momentum conservation and energy conservation. Okay, so this way of studying the dynamics, it's called molecular dynamics, and you can implement it on a computer. And it's very close. It's actually the real dynamics of the system. So once we have a dynamics, what we can do is to try to study what happens when you do a compression. Okay. So you start from a given diameter of the spheres, and then you increase the diameter, for example. So the diameter at time t will be the initial diameter plus some gamma, some compression rate gamma times the time. So this gamma is not the strain that I defined before. It's completely another quantity. Okay. And so what I would like to do is to first study the adiabatic compression protocol. Which means that gamma tends to 0. Okay. So what I'm doing is that I'm compressing very, very slowly the system. Okay. So in order to understand what happens to the system, what you can define is a reduced pressure. So of course you have a pressure that is just the momentum that is transferred to the walls of the container, and you can define a reduced pressure, small p, that is just given by the pressure times beta divided by the density, and beta is 1 over the temperature. Okay. And so what you can do is to monitor the evolution of the pressure, the reduced pressure, as a function of the packing fraction. Okay. So at small packing fraction, the pressure is very low. Okay. And then when you increase it, the system follows the equation of state of the system up to some density here, to some packing fraction, where actually the system jumps to a crystalline structure. Okay. So there is a first order transition. And here the system goes into a crystalline state. And now if you keep compressing, then you compress the crystal. And then at some point, the pressure diverges at the density of the gemmed crystal. And here, if you are in 3 dimensions, the crystal is the face-centered cubic lattice. It's a structure that is, it's a crystalline structure. And the density is close to 0.64. Okay, so this density here is the melting density of the crystal. And this is the freezing of the liquid. Okay, so this is what happens in 3 dimensions. So the first question is what happens if you go to higher dimensions? And this is an interesting question because it turns out that we know the existence of the crystal in only few cases, in 1, 2, 3 dimensions, 4 dimensions, and 24. And this is, sorry, 8 and 24. And this is a very recent result. So what happens when you take a system in, for example, in large dimension? This is not known. It's not known what is the crystalline structure where the system can go. But the most important thing is that reaching a crystalline structure becomes more and more difficult. And this is a kind of dimensional curse in the sense that when you increase the dimension, you expect that the crystalline structure is a very peculiar structure, and you have a very large phase space that is just due to the fact that you have a large dimension. And so what happens when you increase the dimension is that if you run a numerical simulation, like the molecular dynamics that I told you, it becomes extremely difficult to form a crystalline structure. Yes?
To what extent is this plot independent of the speed at which you compress?
Well, it depends on the nucleation rate of the crystal. So I will go to the finite compression rate right now. Okay, so this is what happens if you take an adiabatic compression rate. Before I go to the finite compression rate, let me underline that what you can do is to take, for example, a polydispersed system. So instead of taking all the spheres with equal diameter, you take spheres with many different diameters. And then there, it's even more difficult to define a crystalline structure. Okay. So in a sense, you are adding disorder to the system because then if you take a very polydispersed system, it's not clear what is the crystal. Okay, so now I discuss what happens when you take a finite compression rate. So in this case, if you compress the system fast, and I do not want to enter into details on how fast you have to compress it, but if you compress it fast, what happens is that you can avoid this crystallization, and the system here can be continued in a metastable branch. Okay. that of course it's metastable with respect to the underlying crystal. And now what I would like to do is to understand what happens in this metastable branch. So a simple dynamical observable that you can define is the mean-square displacement. So this is defined in terms of the positions of the spheres, and it's defined in this way. So it's just you can think about it as a kind of distance between the configuration of the system at time 0 and the configuration of the system at time t. So when you fix the pressure, you can plot, so at fixed pressure you can plot the evolution of the mean-square displacement over time. And the typical thing that you see is the following. So at short times, the mean-square displacement increased in a ballistic way. So I plot it in a log scale. So this is t squared. And then if you are at low pressure here, then the system saturates to a diffusive behavior. Okay. Now it turns out that when you are in this regime and you compress the system, at some point this quantity starts to develop a plateau. And then it diffuses. And when you continue to compress the system, so this is compressing the system, this plateau, the length of this plateau increases. Okay. And then at some point, its length actually reaches the simulation time scale, so the time that you can wait in order to see the system to relax. So when the system reaches the diffusive regime, you can think that it has relaxed. Okay, it has gone to equilibrium. It has equilibrated. But of course, this is not true if it is stuck to a plateau. And the physical interpretation of the appearance of this plateau is that actually when you compress the system here, and you are on these time scales, okay, such that the system is in this regime, what happens is that if you look to the real dynamics, you have just the spheres that are basically placed at random, and they just vibrate inside this amorphous structure. Okay, so the high of this plateau that I call delta EA, and I will tell you what this means maybe in the next lectures, just gives you the typical size of the vibrations of the spheres inside these cages, okay, inside the cages that are formed by the surrounding ones. Okay. So once you see this plot, what you can do is to define a kind of relaxation time that is, roughly speaking, the time it takes to the system to reach the diffusive behavior. And the relaxation time, you can collect the data for the relaxation time, and you can fit it with typically an exponential behavior. And you can see that it can diverge at a particular packing fraction. Okay. So anyway, apart from the typical form of the fitting function, what happens is that when you compress slightly the system, so you just increase the pressure slightly, the length of this plateau increases a lot. Okay, so just by a very small compression, you increase the relaxation time by an exponential factor. Okay. Okay, so so you can define the glass transition point as the point where this relaxation time exceeds some cutoff value, okay? That can be, for example, your simulation time scale, okay? And so what it turns out that the point where this relaxation time is large enough depends on the compression rate on gamma. So if your compression rate is small, it turns out that the relaxation time is such that you leave this metastable branch at a given point here, okay? So if you decrease, for example, the compression rate, what you see is that you are able to equilibrate the system a little bit more. Oops, sorry. Just this one. But then at some point, you reach a point where your compression rate, gamma to the -1, is just, what do I have to say? It's smaller than the relaxation time. And once you are in this regime, you leave the equation of state here, and you just go out of equilibrium. So the system is not able to reach the diffusive behavior, and it's not able to relax to equilibrium. Okay. So in this part here, the system is out of equilibrium in the sense that it's not following this equilibrium equation of state. And what we say is that it's in a glass state. Okay. So these lines here are just the equation of state of different glasses that have been prepared with different compression rates. Okay. So the first thing is that this point, that is the glass transition point, it depends on the compression rate. Okay. So the slower the compression rate is, the higher the glass transition point is. Okay. So once you are in a glass, the spheres just vibrate inside this amorphous structure. And now what you can do is that you can keep compressing the system, and eventually, at some point, here, you reach the jamming transition. That again depends on the compression rate. Okay. So once you jam, the system is in a jammed amorphous structure. So you can think that you have just particles in contact. And you can analyze the statistical properties of these packings. And you can find that all packings produced in this way have similar features. And I will tell you what they are. Okay. So jamming of R-sphere glasses. So the first property of this amorphous structure is that, so what you can do is that, so you have a jammed packing, so the spheres are in contact. And they form a contact networks. So this is just the network of spheres that are in contact. So what you can do is to compute the average degree of this network. And what you realize is that the average degree of the contact network that I call Z is 2 times the dimension. So for d equal to 3, it's 6. Okay, so this means that typically each sphere is in contact with 6 other spheres in 3 dimensions. And this property is called isostaticity. And I will describe it in the context of the perceptron. Okay, the other thing that you can do is that you can measure the forces that are exerted by spheres that are in contact. Okay, so for each contact you have a force, and you can draw the histogram of the contact forces. And it turns out that if you look at the distribution of contact forces, for small forces, this distribution has a power law behavior with a critical exponent theta. The other observable that you can look at is the distribution of small gaps between spheres that are not in contact. Okay, so you define a gap between 2 spheres, I and j, as just xi minus xj minus the diameter. Okay, so if I have a monodispersed system, this is just the diameter of the sphere. And of course, what you can do is that you can plot the distribution of these objects, and you discover that the distribution of h for small h goes like has a power law behavior with another critical exponent here that is gamma. Okay, so this is for small gaps. So the fourth property is actually more related to how these amorphous gem structures are reached. So let's come back to this plot here. So once you are in a glass, you never see this diffusive behavior, and the system is stuck here. Okay? And now what you can do is that you can see what happens when you look at this plateau as a function of the pressure. Okay? So you start to increase the pressure, and what happens is that this plateau just goes to 0. So we'll see something like that. And the reason is simple to understand. So once you are in a glass, you have just spheres that vibrate in the structure. And if you compress the system, the amounts of vibrations decreases. Okay. So since the height of this plateau is just giving you how much the spheres vibrate, when you compress the system, it's natural that this plateau goes to 0. Okay. And it turns out that this plateau, delta A, goes to 0 with a power law in the pressure. So at jamming, the pressure diverges. And so this plateau goes to 0 with a power law of the pressure. And this is another critical exponent. So we will compute this critical exponent using the random perceptron problem. Okay. So this is the phase diagram, the phenomenological phase diagram of R spheres. And now the question is, can we understand what drives the phase transition here? What drives the freezing transition? Okay, so there are many different theories of the glass transition, and I will not review all of them, but I will focus on one in particular that is called the random first order transition theory. Okay. So this was started by Wallines, Kirkpatrick, and Tirumalai. At the end of the 80s. And the reason why I would like to discuss this theory is that actually you can show that this theory describes R spheres when you take the large dimensional limit. Okay. So I would like just to give you some references for that. So there is a review that was written by Charbonneau, Couchman, Parisi, myself, and Zamponi. So it's annual review of condensed matter. And it appeared this year, where actually we describe how this solution is derived. Okay, so what I would like to do is to try to describe the phase diagram of R spheres in large dimensions and describe all the phase transitions that can be computed. Okay. Okay, so the way in which you can solve the theory in the large dimensional limit is to join liquid theory and spin glasses with spin glass theory. Sorry, plus. So I will not describe how this is done because I mean I need to at least to introduce tools of liquid theory, tools from spin glasses I will describe in these lectures. But let me tell you what is the emerging phase diagram. So when you go to large dimension, you can define a reduced packing fraction, a scaled packing fraction. Let's say this is 2 times d divided by d. And a scaled reduced pressure is just P over D. And you can plot a phase diagram here. Here I put 1 over the scaled pressure versus the scaled packing fraction. And the phase diagram is the following. So if you start at low packing fractions, you are in a kind of liquid state, and then the pressure increases. Okay. And this line is the equation of state of the liquid state. Okay. So there is a phase transition here that I call a dynamical transition. And this signals the appearance of glassy states. So this is just the phase diagram that I wrote before. I just rewrite it here. So here I was putting the pressure as a function of the packing fraction. This is the crystal, and this is the continuation of the equation of state of the liquid phase. So here we do not have the crystal, okay, and this is just due to the fact that we don't know the crystal structure in large dimensions. So we will never see the crystal here, and you can you have to understand that this branch here is just this branch, okay? Okay, so this phase transition here is called, in the context of structural glasses, it is called mode coupling transition. This is structural glasses. It's called dynamical transition. In spin glasses. And actually, I think that the proper way to call it is an ergodicity breaking transition. So what happens at this point is that if you look to the behavior of the mean square displacement, and you take the long time limit, this is finite. So it's just realizing the fact that when you approach this point, the mean square displacement doesn't diffuse, doesn't relax. Okay. And so since you have this, what you can show is that the relaxation time at this point here, it diverges with a power law. Okay. So here there is a dynamical transition in the sense that the system is not able to relax to equilibrium anymore. Okay. So okay, so in order to describe what happens at phi d, so let me write a kind of picture. So mean square displacement here. Okay, so when you are in the liquid phase, if you look to the phase space of the system, you can see that you can dynamically, you can in principle explore the whole phase space. And this is due to the fact that if you look to the mean square displacement, it can diffuse. So you have, again, a ballistic behavior here, followed by a diffusive one. And if you look in real space, and you look to the real dynamics of the spheres, you can just see that the spheres can escape the cages that are formed by the surrounding ones. Instead, when you are in a glass, so when you cross this dynamical phase transition, the phase space gets clustered. Okay, so what happens is that the phase space is clustered with a large number of, in a large number of regions here. It turns out that if you start the dynamics of the system from in one of these regions, then it's very hard to go to the other ones. Okay, so we'll be confined in a limited portion of phase space. That's why it's called ergodicity breaking phase transition. And this is reflected by the behavior of the mean-square displacement. That is just stuck to a plateau. And you can interpret the sides, you can assign a sides to these clusters that is just given by the height of the mean-square displacement. And in real space, what you will see is that actually the spheres are just caged, and they just vibrate inside their cages. Okay, so the important thing is that you can count the number of these clusters. Let me call it n. And actually, this n scales exponentially with the system size. So you can define a configurational entropy, sigma, that is just the limit so this is the configurational entropy. So the configurational entropy just tells you how many clusters you have. And each cluster is an amorphous structure. So it's just telling you how many amorphous structures you have in which you can be trapped dynamically. And the behavior of this quantity depends on the packing fraction, phi. Okay. And if you look to the behavior of this quantity, it turns out that it's like this. So for packing fractions that are below the dynamical one, so here you have just one state, that is the liquid state. Okay. So once you cross this point, you have many states that appear, many clusters. And indeed, sigma jumps to a finite value. Okay. And now when you increase the packing fraction, this quantity decreases. Okay. And it goes to 0 at what it's called the Couchman transition point. Okay. So the definition of the Couchman transition is that the configurational entropy is 0. Okay? So if you look to the free energy of the system, when you cross this point here, the free energy is completely regular. So there is no singularity, which means that from the static point of view, there is nothing that is happening to this point. Okay? So this point can be seen only dynamically, in the sense that you can just see it with a dynamical observable, that is the mean-square displacement. Instead, what happens here is that a real phase transition takes place. Okay, so this is where a static phase transition takes place, and this phase transition is called random first order. Okay. Okay, so when you go to large dimensions, it turns out that this point scales logarithmically with the dimension. Okay. So this phi k is of the order of log d. So once you are here, you are stuck in a in a so-called ideal glass state. And if you compress this state, you jam. So the pressure increases up to jamming. And this point is called glass close packing. Okay. And what is the meaning of this point? So this point is just a point where, beyond which you cannot find any amorphous structure that is jammed at higher densities. Okay. So this is the point where it's impossible to find amorphous jammed packings at densities that are above this one. Okay. So this is a kind of sat-unsat transition. Okay, so let me try to write it maybe there. So for phi less than phi GCP, you can find amorphous jammed packings. He said for phi greater than phi GCP, this is impossible. So phi GCP is a satisfiability transition point. Okay. Okay. So the last thing I would like to tell you.
I'm sorry, I missed the point. What's the GGP? What's the?
It's called glass close packing.
Yeah, what does it mean?
So if you are below this point, you can find amorphous structures at that density. Okay. So if I fix the density, I know that there is a realization of the packing at this density. Okay. Beyond this point, this is impossible. So you cannot find amorphous jammed packings at that densities. Okay. Unless you overlap the spheres. Okay. So below this point, spheres are non-overlapping. And beyond this point, you can only find configurations at the densities with overlapping spheres. Okay. So if you want to satisfy the constraint that all pairs of spheres are not overlapping, you are constrained to this region. Okay. Okay. So the last thing I would like to say is what happens along this line here. So along this line, so this is the glass face, right? Because when you cross this dynamical transition, you have that the phase space is clustered, and each cluster is a glass. Okay. Now what you can do is that you fix a density here, you initialize the dynamics inside one of these clusters, okay, and then you start to compress the system. So what happens in this case is that the system leaves this equation of state, the equation of state of the liquid structure, and follows the evolution of this glass state upon compression. Okay. And if you do that, at some point, when you are compressing this glass, the glass shrinks, and then at some point it jams. Okay. So this is the jamming point of a glass state that was prepared to a packing fraction phi g. Okay. So this is realizing what I was telling you before in the phenomenological phase diagram. I rewrite it here. So in this metastable branch, you could find different glassy states depending on the compression rate. So if you take a fast compression rate, the system gets out of equilibrium at this point. And if you take a slow compression rate, then the system gets out of equilibrium at higher densities. So here you have just the same thing. The only point is that actually the relaxation time diverges here. Okay. So in order to see this equation of states, you have to initialize the dynamics inside one of these clusters. Okay. Okay. So this is the phase diagram in large dimension. So when you go back from this phase diagram to finite D, the first thing that you realize is that this picture is not possible. So it turns out that if you have finite range of interactions, it's not possible to have an exponential number of metastable states of clusters. Okay. And this is due to the fact that if you are in finite dimensions and you have finite range interactions, you can always nucleate the stable phase, that is the liquid phase. You can always enucleate it. Okay. So it's not possible to have an exponential number of metastable states. What is possible, but we don't know if it's the case, is that you can have a phase transition here where the complexity is the configurational entropy is 0. Okay. So this is the only point that can maybe survive infinite dimensions. Okay. So I think that we can make a pause. So this is the last thing I wanted to tell you about structural glasses, and then in the next hour I would like to discuss constraint satisfaction problem and make the analogy between the two. So now I would like to jump to constraint satisfaction problems. Okay, so let me give the general structure of our constraint satisfaction problem. So you first need to have a set of variables. Let me call x the set of variables. And these variables take values in a given set, S. Okay. Then you define a set of constraints. So these are variables. So each constraint is as an index alpha. So you have m constraints. So alpha goes from 1 to m. And in order to define it, you first define a subset of these variables. So for each alpha, you have a subset x alpha, and this is formed by a subset of these variables. So you have x1, xk alpha, okay. Okay, so this means that x alpha, so if xi is inside this, then x alpha is inside S to k alpha. Okay, and then a constraint is just a function, psi, that goes from S, let me call this alpha, from S alpha to 0, 1. So it's a binary function. And then you say, so psi alpha of x alpha is equal to 1 if the constraint is satisfied. And it's equal to 0 if it is unsatisfied. Okay, so the CSP, the constraint satisfaction problem, given the nature of the variables, which means given the set in which they take values, and the nature of the constraints, the constraint satisfaction problem is just to find an assignment x for the variables such that all these constraints are satisfied. So what you can do is, so the CSPs find an x such that the product okay. So a very nice way to represent a CSP is to use a factor graph representation. So each variable xi, you denote it with a circle. And each constraint alpha, you denote it with a square. And so you define that variable node and so this coincides with psi alpha. And a check node. Okay, and if this variable enters into this constraint, which means that if the variable xi is part of this subset x alpha, then you put a link between the variable and the constraint. Okay, so when if you have all the constraints, you have. Using this rule, you can construct a graph. Okay. That tells you which variable is in which constraint. Okay. Okay, so an instance of a CSP is defined by three things. So the first thing that you have to define is S. It's just the set where the variables take values. The second thing that you have to define is the nature of the constraints. So you have to define this function. And the third thing, so second thing, nature of the constraints. And the third thing is the factor graph. So which variable is in which constraint. So you can have different kinds of CSP. So first of all, the first example is a decision problem. Which is just given a CSP, given a constraint satisfaction problem, tell if there is a solution or not. Another question that you can ask is sampling. So if there is a solution, then find one. Okay. And the third one is optimization. So in the case in which there is no solution, okay, find the configuration of X that has the minimal number of unsatisfied constraints. Okay, so you want to minimize the number of unsatisfied constraints. Okay, so given the CSP, what you can define is the volume of solutions, and I call it Z. And the reason why I call it Z will be clear maybe the next lecture. And this is just given by X. Sorry. And then I have okay, so this is the volume, the number of solutions. And in particular, Z is greater than 0 if you are in the satisfiable phase, so if you have solutions to the problem, and Z is less than 0, so sorry, is equal to 0 if you are in the unsatisfiable phase. Okay, so CSPs are typical problems in computer science. But what people in computer science are used to is to analyze CSPs from the so-called worst-case scenario. Okay, so in the worst-case scenario, what you would like to understand is how complex is the most difficult instance of the problem. Okay, so there are two scenarios. The first one is the worst case. That is typical in computer science. And so what you are asking in the worst case scenario is, given the CSP, you want to know how much it is difficult to find a solution given the most difficult instance of the problem. Okay. The other scenario is the typical case scenario. And this is what can be analyzed in statistical physics, I would say. So what you do in this case is that you think about the CSP as being extracted from an ensemble of instances, okay? And then what you ask is a typical instance of the problem, is it satisfiable or not, okay? So you extract at random a given instance of the problem, and then you ask, is this typical instance satisfiable or not? And so this one is what we can study using statistical physics tools. So in order to understand these things, I would like to focus on a particular constraint satisfaction problem, that is the random coloring. So this was analyzed a lot by Lenka. Laurent. So let me define the problem. So the set S is given by n values. So xi, it's given by q values. So xi can take q values, 1 up to q, and q is the number of colors. And now I fix, so each constraint, psi alpha, depends only on two variables. So what I was saying before is that x alpha is x1 xk alpha. And for all alpha, k alpha is equal to 2. So each constraint depends only on two variables, x1 and x2. Okay. Okay. And now this function is very simple. So it's just 1 minus delta okay. So what you want is that if these two variables are inside this constraint, you want them to be different, okay? Because you want that psi alpha is equal to 1. Is it clear? Okay. So we have fixed the set S. We have fixed the nature of the constraint. And the last thing that we have to fix in order to have a well-defined CSP is the factor graph. So it's just the network of interactions between variable nodes and checks. Okay. So there are two possibilities. So what you can do is to extract the factor graph from a given ensemble of random graphs. So you have two possibilities. The first one is Erdos-Renyi random graphs. So in this case, what you do is that, so for each constraint, you need two variables, right? So you have n over 2 possible couples, and you extract m couples from them, okay? And you define, given these m couples, you define the constraints, okay? So you have n over 2 couples of variables, you extract m, and at each one you assign a constraint. Okay. So the interesting thing is to extract, since what we want to do, okay, a thing that I didn't say is that what we can do in statistical physics is to study what happens to these problems when the number of variables, n, goes to infinity. This is a kind of thermodynamic limit. And here, in this case, what you can do is to define this problem with a number of constraints, m, that goes to infinity. And in particular, what you would like to do is to fix m such that this is some constant times n. So if you do that, it turns out that a given variable enters in a variable number of constraints, and the number of constraints in which this variable enters, let's call it C. This is just the connectivity of the variables. This is a Poisson number. So C is Poisson distributed. And the average value is just given by 2 times alpha. So this is the first ensemble of random graphs. There is a second possibility. There are random regular graphs. So in this case, what you do is that each variable enters in exactly C constraints. Okay. So now C is not a random number, but it's just fixed. Okay. And then what you do is that you extract at random with a flat measure all factor graphs that have this property. So C here, it's fixed. Okay, so once you define the random graph ensemble, you can generate constraint satisfaction problems. And you can analyze if they are satisfiable or not. Okay, so here in this case you have 2 control parameters. So so the first one is the number of colors, okay, Q, and the second one is C, and C can be either the connectivity in the random regular graph case or the average connectivity in the Erdős-Rényi case. Okay, so what we will do here is to fix Q to a value that is greater or equal than 4. What happens for values smaller than this one, it's a bit different. So the phase diagram that I will describe is really, it's what you get in this case. In the other case, it's different. So I don't want to enter in the other case. So let me fix Q greater or equal than 4. And now what I would like to understand is what happens to typical instances of the problem when I change the connectivity C. Okay. So what you can expect is that if C is very low, then it's very easy to find a satisfiable assignment of the problem. Okay. But then when you increase C, there is a point that is a satisfiable transition point where the probability that at a typical instance of the CSP with connectivity greater than this critical connectivity, so the probability to find a satisfiable assignment goes to 0. So this is the SAT thresholds. So I just repeat. So for C less than this critical value, you can find with probability 1 a satisfiable assignment for the CSP. And if C is greater than this critical value, the probability to find a satisfiable assignment goes to 0. Okay, so the way in which we can analyze these problems is to define an energy cost function.
Sorry, you mean goes to 0 when n is large?
Yes, in the thermodynamic limit. Okay. Okay.
You said that before CS is 1, the probability?
Yes. So
What does this mean?
that if you sample a typical instance of the problem, the typical instance will be satisfiable. And you can find a solution. I mean, in principle, you can find a solution. Okay? So in order to study this problem, you can define an energy cost function. So this is just this. So given a configuration X, you define the sum over all the constraints So what this is doing is that it is just counting the number of unsatisfied constraints, because if this is satisfied, psi alpha is equal to 1 and you get 0. Okay? Whenever you have an unsatisfied constraint, this is 1. So this is just counting the number of unsatisfied constraints. And so if you plug the expression for psi alpha, you get that this is the sum. Okay, let me do it carefully. So if psi alpha of x was 1 minus, let's say 1. So in this case, my factor graph is like this, right? So since each constraint contains only 2 variables, I have a factor graph that is like this. So the squares just contain 2 links. So I can just replace the squares with links. Okay. And if I do that, I have just something like that. Okay. So if I plug this expression in this one, what I get is just the sum over nearby variables, so variables that are connected by a link of delta xi xj. And so this is just the Hamiltonian, the energy of an antiferromagnetic Potts model. Okay, so this is on a random graph. Okay. So once you have an energy, you can study the Boltzmann measure. So you can do the statistical physics of the model. And why you want to do that? So suppose that you want to solve the constraint satisfaction problem. So what you can do is just try to do a simulated annealing. So this is analogous to the compression protocol that I was discussing for our spheres. So you interpret the variables x as dynamical variables, and then you run the dynamics, a thermal dynamics. Okay, so for example, Monte Carlo dynamics at a given temperature T. Okay, and now what you want to do is that you want to decrease the temperature in order to find the ground state of this model. So if the ground state is 0, then you have found a satisfiable assignment. Otherwise, the configuration that we have found, it's the configuration with the minimal number of unsatisfied constraints. So you can do that. For example, you just do a Monte Carlo simulation. And once you fix T, you have a phase diagram. Here you put the temperature, and here there is the connectivity. See? And in this phase diagram, there are phase transition lines. So I will just draw it and then I explain it. Sorry. Okay. Okay, so what you do is that you initialize the dynamics starting from a random configuration, which means that you are at very high temperatures, and then you start to cool the system. You decrease the temperature, and then it turns out that if you fix the connectivity here, when you cool the system is able to find an equilibrium configuration at that temperature only up to a point here. Okay, so this line is called a dynamical transition line. So when you reach this line, the Monte Carlo algorithm is not able to find an equilibrium configuration anymore. And so this is exactly the same transition that I was discussing before for our spheres. So it's a dynamical phase transition. And if you go to, so suppose that you start from here. So below this point here, you can really reach zero temperature equilibrating the system, and indeed you can find satisfiable assignments to the problem. When you cross this point here, it happens that you have the same phenomenon that I was describing before for our spheres. So here, the space of solutions gets clustered. So let me draw another phase diagram. So here I put C, and here I put CD, CK. So if I look to the space of solutions to the CSP, below CD, this forms a unique cluster, okay? And actually, if you find one solution, you can move locally to find other solutions. When you cross this, this point, the space of solutions gets clustered, okay? So you have islands of solutions. And if you start from one of them, you can explore it just by local movements, just by local changes of the variables. Okay, but these solutions are disconnected, so you cannot go. If you have found a solution here, it's very hard to find another solution that is inside a different cluster. Okay, and the number of these clusters actually is exponential in the system size. So you can define sigma again, that is just 1 over n, the log of the number of these clusters, and it behaves the same as before. So if I put sigma here, at this point, sigma is finite, and then it decreases when you reach this point. So this transition here, it's called clustering transition. But it has the same nature of the dynamical phase transition that I was describing before for our spheres. Okay, so when you increase the connectivity, it turns out that the clusters of solutions rarefy. So the complexity decreases, and then at some point here, at this transition point, the number of these clusters is sub-exponential. Okay, so this transition here is called a condensation transition. And so beyond this point, the solutions are in a number of clusters that is sub-exponential. So when you keep increasing the connectivity, at this point here, you cannot find any more satisfiable assignments. And so here you enter in the unsat phase. And if you plot the energy of the system here, the energy grows. Okay, so this is E of C. So the ground state energy starts to become different from 0. Okay, so you see that there is a very deep analogy between glasses and these constraint satisfaction problems. And let me be more explicit.
Sorry.
Yes.
When you say that the n is sub-exponential, so I have less clusters, but what about the size of the cluster?
Yeah, the size of the cluster is finite here.
It's finite.
You have, so if you look to the internal structure here, you have a finite entropy, internal entropy. So you can assign at each cluster an internal entropy that is just the log of the number of solutions inside the cluster, and this is finite. And actually it's finite up to here.
Okay.
And it doesn't go to 0 here. This is very important. But I will discuss it in a while. So there is a formal analogy. So let me consider R spheres and CSP, so random coloring, Q coloring. So this is how computer scientists call this problem. So you see that CD is analogous to phi D for R spheres. CK is exactly the same of the Couchman transition point. And CS is analogous to phi GCP, to the glass closed packing point. So here, it's where the complexity sigma. So here, what in glasses is called the configurational entropy, here it's called the complexity. Okay. So complexity or configurational entropy is exactly the same thing. So here, sigma is greater than 0. At this point, sigma becomes equal to 0, and this is the RFOT transition, the random first order transition. And this is the satisfiability transition point. So this is the SAT. The SAT and SAT transition point. So the interesting thing that one can note is that the satisfiability transition point is inside the glass phase. So this is the glass phase, right? In both cases, here and here, the satisfiability threshold is inside the glass phase. So if you want to compute it, you have to understand how to compute the properties of these clusters. Okay. So these are the similarities. And now let me draw the differences. So our spheres, you call. So if you take our spheres, there is no quench disorder. In the sense that the interaction potential doesn't depend on any random variable. Instead, here, there is disorder. So where is disorder here? The disorder is in the random graph. So you have a random graph that is just giving you a set of random interactions between the variables, and the randomness is just in the links, okay? And this is quench disorder, okay? So this is the first difference, and the second difference is that here you have continuous variables. Because the positions of the spheres are continuous variables. And here you have discrete variables. Okay. So what I would like to do now is to do a kind of mix between these two problems to define a new one. And so I will consider a problem where you have quench disorder, but you have continuous variables. Okay, so let me define this problem. So this problem is the spherical random perceptron. Okay, so this is a constraint satisfaction problem. It's a CSP. So the perceptron is a model, a very important model if you in machine learning. It was introduced a long time ago by Rosenblatt as a model of a neuron. But in this context, we will transform it in a constraint satisfaction problem. Actually, this is a good model, a simplified model to study the jamming transition, and this was realized by Franz and Parisi. Actually, in 2015, I think. I don't remember. Yes, I think 2015. So let me define the model. The model is the following. So first we define the variables. So again, we have x. It's a vector. So xi are real variables, but they have to satisfy the spherical constraint. So the sum of from 1 to n of xi squared is equal to n. So we have n variables, and here n goes to infinity again. So these are the variables. And now I define the constraints. Okay, so let me introduce an index mu that goes from 1 to m, and m scales with n with a proportionality factor that is alpha. So this is a control parameter of the problem. So for each mu, you extract a random vector. Okay, so let me write it here. So for each mu, you extract a random vector, xi mu, so this is an n-dimensional vector, and xi mu I are just normal Gaussian variables. So they have zero mean and unit variance. Okay, so given these vectors and the variables, you can define a gap variable. That is h mu. So for each mu, you define this object, this 1 over square root of n psi mu dot x minus a constant, sigma. And this is another control parameter. Okay, of course, since these are random variables, this product is of order square root of n, so this object is of order 1, and this control parameter is of order 1. Okay? Is it clear? So the CSP, the constraint satisfaction problem, is defined in this way. Find x such that for all mu from 1 to m, h mu is greater than 0. Okay, so you have n variables, n constraints for each vector mu. I will call these vectors patterns. And this terminology comes from a neural network. So for each pattern, I have a gap variable. And the constraint is that this gap variable must be greater than 0. Okay. So let me define an energy cost function. So I define the energy cost function in this way. So for each unsatisfied constraint, so if h mu is negative, then this theta, this is the EV side theta, this theta is positive. So if the constraint is unsatisfied, then I pay an energy, I pay a cost, and the cost is proportional to the square of the gap. Okay? Okay, so this is the energy cost function. And let me draw the factor graph. So I have n variables, 1, n. So this is x1, this is xn. And then I have m constraints that are defined by the patterns. And since here you have a scalar product, you have that each variable enters in all constraints. Okay. Okay. So this is a fully connected model. Okay. And now let me start to in the last 5 minutes, I would like just to discuss the analogy between this model and models of spheres or R-spheres. Okay, so suppose that you take again spheres, and now I made them soft, so that I say that I pay energy if the spheres overlap. So if I have two spheres at position xi and xj, then I can define a gap variable between the two. That is just xi minus xj minus the diameter. Okay. So hij is negative if the two spheres overlap, and it's positive if they don't overlap. And so this is the soft sphere model. Is a relaxation of our spheres. And you can define an Hamiltonian that is just analogous to this one. Okay, so you just pay energy when the spheres overlap. And now you see the analogy. The analogy is that this parameter sigma is just playing the role of a kind of diameter. Okay. So the analogy can be made more formal, slightly more formal. So let me draw the phase space. Maybe I can do it. No, I can do it here. So the vector x lives in an on an n-dimensional sphere. Okay, this is a sphere of radius square root of n. Yes. And so on this sphere you have the vectors, the patterns, xi mu. So let me draw one. And now the constraint can be interpreted in this way. So you want that h mu is greater than 0, which means that 1 over square root of n of psi mu dot x is greater than sigma, which means that this scalar product should be greater than square root of n, sigma square root of n. Okay, so you just draw. So now you have two cases. So if sigma is greater than 0, then what you have is that x must be in this cone, right? So here, this quantity is square root of n times sigma. And so a solution for this constraint would be a vector x that is in this region. Okay. And now you have m vectors. And so the constraint satisfaction problem is just find the intersection of all these domains. Do you agree? And now the problem is that when sigma is positive, all these domains are convex. So you have the intersection, the CSP is the intersection of convex and so you know that the intersection of convex domain is convex. And so what you have in this case is that the space of solution is just an island, one island on this sphere. Okay. Now let me consider the other case where sigma is negative. So if sigma is negative, what you have is the following. So again, you have the sphere, then you have a vector psi, in general it's like this. And if sigma is negative, then so this quantity again is square root of n times sigma. But now the solution, you accept the solution. So a vector x that satisfies the constraint mu is on this space here. There is no convex. And so in this case, the problem becomes the intersection of non-convex domains. And so this makes the problem different in the sense that when you look to the intersection of non-convex domains, you can have islands of solutions, and they are disconnected. So in this case, you could have that depending on the control parameters, and we will see that this is the case, the space of solutions gets clustered, okay? And this is due to non-convexity. Okay, so what I will do in the next lecture is to set up the formalists to solve this model and to study the space of solutions of this model. Okay, and what I will do is to build up all the replica techniques that can be used to do this. Okay.